In my last video I made this. I called the project The Sound of Resistance. So what this does is it measures a resistance and then represents that resistance as a sound, with low resistances being a low pitch tone and higher resistances being higher pitch. If you haven't seen that video, I strongly recommend that you check that out, because then you'll know exactly what I'm talking about, hopefully anyway. In the comment section of that video I had a comment suggesting that I could make a similar device using an Arduino. Now I did actually respond to that, saying I didn't think the ADC had the necessary resolution to recreate this device exactly the same. But I went ahead and looked into it anyway, and I actually came up with this. So again, this is kind of an experimental or a prototype device that I'm still working on. Let's go ahead and look into this a little bit deeper. So let's get on with it. As I said in the intro to the video, this device consists of a Attiny85, two LM317 voltage regulators. Each one of those has a resistor for setting the current limit mode. I'll go into that in a bit more detail later. We've got a few capacitors, a couple of switches, a buzzer, and a potentiometer and another current limiting resistor for the buzzer itself. In fact, this resistor and the potentiometer are in series, and they're purely to adjust the volume of the buzzer. I'll start off by actually demonstrating this. Now, it has kind of evolved over the last few days into something a lot more complicated than it initially started out as. So now it actually has basically 4 modes of operation. And I will try to explain those as best as I possibly can with demonstration. After that, I'll probably show you the circuit diagram and explain what I'm attempting to do. I'll then show you the program that I've written for this, and then I'll finalise by actually showing you how to program the Attiny85, which isn't actually quite as straightforward as it could be, but it's not hard, but you just need to make some additional hardware to be able to program this from a USB connection. So let's start by actually demonstrating the unit. So to start with, I just want to demonstrate this piece of wire that you can see on my bench here. So this is actually a piece of resistance wire, and I have it doubled up, so I've actually got approximately 20 ohms between these 2 points here. I'll demonstrate that on the meter. So we've got 19.6 ohms. So then between here and here we've got 9.3, and then between here and here we've got 9.4, and then obviously with the loops at the end, etc., it all adds up. So that's what I'm going to use to demonstrate the device. So it's powered by a USB-C connector. I've got USB-C power here, so it's just plugged into a standard USB charger, and if you heard that, it initially gave a 3 beep tone. So the way this is programmed is if you just plug it in and don't touch anything, it goes into what I call the default mode, which is my favorite mode of operation for this device. So I'm just going to plug some probes in here. So in the default mode, it's as much of an equivalent in operation to the original circuit or the original device as in the previous video. So we'll see that if I start with the probes quite close together, we get a tone, and as I move the probes apart, that tone increases. And then I move them back together again, and it goes down in pitch again. So that's the default mode of operation. Then what I've done is I've also in the software enabled you to change the ranges of operation. So in other words, the resistance range over which the tone changes. Now the reason I've done it that way is because these PC motherboard type buzzers have quite a limited frequency range, and to be able to get a decent range of frequencies I need to be able to keep the ranges relatively small. So I've actually broken that down into 4 ranges. So the way that you change the operation mode is that on initial power up, if you press and hold this button, it will then go through a separate sequence where it will allow you to set the operation mode and also how long the tone is. As the device is now, it's actually in running mode. So any time in run mode, if you press the button, it will actually reset, and that gives a long continuous tone for 5 seconds to indicate a reset. And then if you keep your finger on this button during the startup process, it will then enable you to enter into the mode where you set the scaling and the duration of the tone. The first range being the measurement range. That's determined by the number of presses on the button from 1 to 4, representing mode 1 being low resistance, mode 2 being slightly higher, mode 3 being slightly higher again, and mode 4 being the highest. Once you've entered the number of presses to represent that mode, the buzzer will then confirm that by repeating back to you the number that you entered. That is confirmation of the operation range. After that, it will go into the second entry mode, which is announced by 2 separate tones. After that, it's then asking you to input the time length of the tone itself. So that's in multiples of 75 milliseconds. You will be able to input from 1 press to 10 presses, representing 75 milliseconds to 750 milliseconds. When that is complete, it will then give you a tone representing the length of the tone that you have entered, and after that it will then beep 3 times to tell you that it's in running mode. So it's in mode 3, running mode for this function. Okay, so as a recap, mode 1, indicated by 1 beep, is to enable you to enter the scaling factor for the resistance. Then mode 2, indicated by 2 beeps, will enable you to enter the duration of the pulse of the tone. And then mode 3 is operation mode, indicated by 3 beeps. Now notice when it first powered up, it gives you 3 beeps. So when you first power up and it beeps 3 times and you don't press anything else, that is the default mode. So the 3 beeps are representing the fact that it's in run mode, but the fact that you haven't actually pressed anything, it will be in default settings. Okay, so we'll try and go through that in real time. So I'm going to press the reset button and hold it. So mode 1, I'm going to press the button twice. It should beep back twice. Okay, I'm in mode 2. Now 2 beeps are now in setting 2, so I'll go press once and that should give me a 75 milliseconds bip, followed by the 3 tones to confirm that it's in run mode. So now I still should have quite a short pulse, but in a much extended resistance range, as you can see by the distance that the probes are apart compared to the default mode. Okay, we'll do the same I'll put it into mode 3. So 3 passes, 3 confirmations, 2, and then I'm going to press it again once for 75 milliseconds. Mode 3. So now I should be further up the scale. So yeah, mode 3 is approximately 9 ohms, maybe a bit more. I'd say around there, which is probably about 13 ohms for mode 3. Okay, we'll go into mode 4. Do 75 milliseconds again. Okay, so now we're into mode 4, so again we should be much higher up. So if I start roughly where mode 3 finished, quite a low tone. So this is 20 ohms. Get the wires out of the way. It's not the easiest thing to achieve here. Let's do that again. So we'll start at, this is 19 point something ohms, and we'll go down. So that's approximately 10 ohms. So press reset again, and I'll just show you default mode. So just leave it, go straight into mode 3, operation mode. So this is basically the lowest range with the shortest duration, which is my favourite mode. That's why it's the default. So let's get in so you can see in shot. So we're quite close together on the probes, and we go up in frequency over very short duration, or a very short resistance change. Okay, so that's that, and then we have the additional mode, which is actually mode 4. So it's a run mode, it's mode 4, and we actually need to use the second input for this. The Attiny85 actually has 2 analog inputs, so I thought, well, while I'm doing this, I might as well try and utilize as much of this thing as I possibly can. So I decided to incorporate a simulated diode test function on a multimeter, similar to a Fluke meter, like this one. So I don't know if you're aware. Okay, so we've got a diode here. So if we put a Fluke meter, I think all Fluke meters do this as far as I'm aware. If we put a Fluke meter into diode mode and you short the leads together, it makes a continuous tone. But if you measure a diode in that mode, what you will notice is it tells you the voltage drop across the diode, but it also, rather than giving you a continuous tone, gives you a very short single tone. That's a very good idea. It's a shame all multimeters don't do that, because it enables you to quickly test between or distinguish between a short circuit and a diode without even looking at the meter, which is in a similar vein to the concept of the sound of resistance. So I thought I could incorporate that into this device as well. So that's basically what I've done, but I have gone a step further than that. So I found some diodes. So if we power the device up, And then we need to go into mode 4, and we do that by pressing the other button, and that's confirmed by 4 beeps. And we can see I'm plugged into the connector with the green wire on now, so we're now into diode mode and diode input. If I short the probes together, we can see that we get a continuous tone. And then if I use a regular silicone diode, we get a short tone, very similar to the Fluke. But I've also gone a step further and added the Schottky diode. So if we now do the same with a Schottky diode, see we've got a single tone but it's a different pitch to indicate a Schottky diode. But I've also gone one step further and in other devices that I've seen of this nature, there are specific measurement ranges for both regular diodes and Schottky diodes. But if you have a diode that falls in slightly in between those two ranges, the similar device that I've seen doesn't actually give you any indication whatsoever. It just is silent, which isn't the best. So what I've tried to do is incorporate a system where it will give you a different tone, indicating that that you are actually measuring a diode, but it might be not in the predefined ranges for both a Schottky or a silicone diode. What am I doing here? So yeah, so if I put two Schottky diodes in series, for example, so I mean these Schottky diodes are actually reading just over 0.2 of a volt, so they are well within the bottom end of the range. Now a Schottky diode, according to the data that I've read, can go up to 0.46 volts across the junction. So if I put two of these lower ones in series, there's actually indicating somewhere close to the upper end of a single diode in the tolerance range. And you can hear that it does a double low-high tone. So we've got a single, it's a low tone, and then a double is a low-high tone. And then the regular silicone diode is the higher tone. So that's diode mode. That simulates a Fluke meter in the respect that you get a single continuous tone with a short circuit. You get a short tone with in this case with a Schottky diode, or it's still a short tone but a higher pitch with a silicone diode. And if you have a diode that falls in between the ranges of a Schottky and a silicone diode, then we get a double tone, indicating a diode that falls in between the two ranges. So one of the disadvantages of this system is that the input voltage is not regulated on this circuit that I have. It's designed to run off a standard USB supply, but even with those, the voltage can actually vary a little bit. And one of the disadvantages of this system is that the analog input is actually scaled to the supply voltage. If you have a slightly lower voltage with the diode tester, we're not in mode 4. So we're into mode 4, and then we'll measure the diode. Now the problem I've found is that the actual accuracy of the scaling for the various or for the different types of diode can vary a little bit with the supply voltage, because the input to the analog to digital converter is actually scaled to the supply voltage. So therefore, if your supply voltage varies, the actual values that you're measuring as your input will depend on the supply voltage also. That is the same for both the diode test mode and the input mode, but as that device is just more of a comparator or comparison device, that doesn't necessarily cause you any issues. But when you're measuring absolute values, as in measuring a diode, then the input voltage can have some effect on that. I have added a couple of different values in the comments on the program, which I will show you later, which should give you some half decent values for a couple of different input voltages that I've noticed when testing this device. So I just want to do a few more demonstrations here. So I'm currently in mode 3 with a 75 millisecond duration. Mode 2, .75 millisecond duration. And we're in mode 3, which is run mode. So then lower. Should be able to do a sweep. Mode 1. That should be a 300 millisecond. We're going to mode 3 into run mode. So for example, so we're in mode 1, so we're looking at very low resistances. Now the reason you can hear the different tones is that, in my opinion, obviously, that the A to D converter in this guy is very inaccurate at very low ranges. That's the downside of not having any additional analog circuitry in this system. The input to the analog to digital converter is at very low voltage, and therefore there's a lot of errors in this conversion at that low voltage. So I have incorporated into the software some averaging to try and eliminate those errors as much as possible. And the higher the range, so for example in mode 4, which is the highest measurement range that I've got this configured for, there is actually no input averaging whatsoever. It's a direct input, and you'll see that it's a lot more stable in that condition than it is measuring the very low voltages. And to demonstrate that, we'll go into mode 4. So it's 4 presses, 4 bits for confirmation. In mode 2, 1 bip for 75 milliseconds, which is confirmed by the short pulse. Mode 3, so now we're measuring higher resistances. there's no input averaging on this whatsoever. You can hear that the tones are much more stable than they are lower down the range. So this is the program itself. I've called it Tiny Sound of Resistance because it's based on the Attiny. If you're not familiar with Arduino programming, this isn't going to be a full tutorial on how stuff works. I'm just going to go through the various sections that I have written in this program to do the various functions. For those who are familiar, we've got some, all at the start of the program, I've got the definitions of variables here. They are the hardware definitions for the input pins, and then we've got some definitions for time durations for entry of the data. We've got a definition for the duration of the short beep, for the double beep, and then we've got the definitions which determine the program's determination for the value of a short circuit, the value for a Schottky diode, a silicone diode. We've got the measurement array length, then we've got the frequency ranges for the high and low tones for the diode test, and then we've got the frequency ranges for the sound of resistance test. So we've got the range 1, range 2, range 3 and range 4 as I described it earlier. So if you press the button once, for example, and you get a single tone, that's selecting scale 1 or range 1, which is 1 to 10. So scale 2 is 10 to 50, scale 3 is 50 to 200, and then 4 is 200 to 400. We've got some variables here for just for timing and for arrays, and then we've got some control bits for the various sections of the program. Okay, so then we go to the setup section, and basically that's just defining the analog inputs and the digital inputs, and then it's running the startup program. So in that program is actually the actual setting up of the software. You'll see there's all the comments will describe exactly what's going on. The startup program then calls the configure program, which then goes through the configuration of the program scaling and the tone length. That's where you set those. We've got the sections for the initial so if you press the second button, for example, it then initialize the diode mode, and this is where that's initialized. Subroutine that actually reads the button number 1 for the push button, how many times you pressed it, the confirmation of that. Then we've got is the same with reading the tone duration. So it's a similar thing. It counts the number of presses and then assigns that to a variable, and then we'll tone out that as a duration. We've then got the section of the program that actually assigns the scaling for the frequency depending on how many presses that you've done. We've then got to bleep if it's a diode, to beep if it's in between, so it's the double pulse, a Schottky diode, and to bleep if it's a short circuit, the analog read for the actual diode mode, and then we come to the main part of the program. So that's basically split into two. So when we set modes 1 and 2, that's actually done in the configuration, hence you have to have press the reset button before you can enter that mode. Once you've done that, then it will set this bit to say that that's complete, and if you're not in diode mode, and if that's complete, then it will scan this program, which is basically reading the analog in sensor and then doing some averaging on that, and then if that's a valid reading, dependent on the scale that you've set. So for example, mode 5 is the default mode, so if you haven't had any input whatsoever, you've just powered the machine on, it will go to mode 5, and that's basically telling it some fixed values for the scaling, a fixed beep duration of 50 milliseconds, and obviously the pitch will be defined by the scaling of the analog read. and then the same thing for modes 4, 3, 2 and 1, which are again the scaling for the sound of resistance mode. Then if we're actually in the diode test mode, so diode test is actually selected by pressing the second button, and that is then toned out as 4 bips to say that you're in the fourth mode, which is diode mode. And then we come into the program that determines what happens if you're in the diode mode. That is obviously using the second analog input as defined in the program, and it basically it's reading the analog input and then determining whether you've got a diode, a Schottky diode, you're in between, or you've got a short circuit, and it will call one of those routines depending on that. I will finish the program comments before I make this program available. So that's basically it. As I said, some values here, I have put some additional values in. The values that I've got at the moment are for an input voltage of just over 5 volts, which is probably quite common for most USB power adapters. So these are the ones that I've actually left in there. These may change a little bit from the video to what you actually see in the final version, depending on further testing. So I've also determined some values for an input voltage of 4.8 volts, which is basically the lowest that I've ever seen from a USB power bank or power adapter. I have seen them go down to 4.8 volts. So these are the kind of values that you'd need in there for 4.8 volts. And the final values that I leave in the program will be the values that will work from sort of 5 to 5.2 volts, somewhere around there. All of these values are obviously configurable. You can, if you wish, change the high and low beeper pitches. You can change the ranges for the sound of resistance scaling. So you can see that I've got a sample size of 12 now. That is the number of samples that I use for the modes 1 and 2, and I believe 3 is used to determine the number of samples that I do the averaging over for the sound of resistance. Again, in mode 4 that is not used, so the highest range. Again, this value here is the time in milliseconds for the calculation per press of the button for setting the duration time. So again, you could change this to 50 if you wanted, but as I've already got the default set to 50, I thought that the next level up would be 75, so that's why it's 75 in there. But you can put it to 60. I mean, you can change that to whatever you want. So there are a few variables in here that you can change should you wish. These are all set to my preferred values. So this is the schematic for the device. So as I explained earlier, we've basically got two LM317s. Now they are configured slightly differently by the fact that this one has a 10 ohm resistor and this one has an 820 ohm resistor. We can see here that these approximate values. So plug 1, which is the input for the sound of resistance, provides a fixed current of 125 milliamps, and that's the one with the 10 ohm resistor. If you're aware, I don't know if you're aware that LM317s have a reference voltage of 1.25 volts. So if you then divide that by the resistance that you put between pins 1 and 2, that will then turn it into a constant current source determined by that factor. So it would be 1.2 divided by 10, which is 0.125, 125 milliamps. And it's the same theory with the 820 ohm resistor. So these are approximate values for constant current sources, which I use then for plug 1 is 125 milliamps for the sound of resistance and about 1.5 milliamps for the diode tester. So that's on pins 1 and 2 here. They go directly into the analog inputs onto the Attiny85 here. Pin 3 just literally connected straight to ground. We have the two push button switches. So switch 1 goes to PB0, which is pin 5, and switch 2 actually So that's a slight mistake on the schematic. This switch 2 actually I have connected to pin 7. I will revise that, but not for this video. So just so you know, that switch 2 is actually connected to pin 7 and not pin 1. Other than that, the schematic is correct. So the output is pin 6, PB1, goes through a fixed 22 ohm resistor and then through a 100k preset. So that gives you some adjustment range on the buzzer. Everything else is done in software, so it's a very simple circuit. We've just got a few bypass and filter capacitors on the board here, and that's it. So again, I have at the bottom here tried to abbreviate the standard modes and the operation. So with switch 1, if you leave at startup, it goes direct to mode 3 with default settings. If you press switch 1 at startup, then you get to select the operation mode. So at startup you press and hold switch 1, that then takes you to mode 1, which enables you to select the scaling factor 1 to 4. Following that, you go to mode 2, which then lets you select the time of the buzz on those modes. So that's selected with a multiple of presses from 1 to 10 presses, which will then give you from 75 milliseconds to 750 milliseconds. And then if you press switch 1 during run, that will actually reset the Attiny85 to restart the program. For example, if you're in the default mode, mode 3, you can press the button to reset it, or then enable you to select your parameters. Or if you've already selected a parameter and you don't press a button, we'll obviously go into default settings. Then during that phase of startup, if you press and hold switch number 2, that will then take you into mode 4, which is the continuity stroke diode mode. So there's an abbreviation of the operation modes. These are the 3 things that you'll need to make the programmer the same way as I make it. As I said, there are much simpler ways to do this, but for the reasons that I will explain in a minute, this is the system that I use. So we need an Arduino Uno or compatible. I've had this one for years, so this is just the one that I'm going to use for this project. We need what's known as an AVR ISP shield. Now, this is identical to the one that I've had for years. So this is the one I've had for many years. This is one that I purchased from AliExpress just a few weeks ago. It's an identical copy. This was, I think, about £1.80 or around $2. And then on top of that, we will need what's called a DigiSpark starter kit. This is for various Attiny microcontrollers, and basically you can't actually program from this. This is basically, in fact, I'll open it up. So let's just zoom in on that. Okay, so basically all this is an 8-pin IC socket, a USB connector, which we're not going to use at all. It's got a few capacitors and resistors and LEDs, a power regulator, but basically I just use this as the socket and an adapter. So what we do is we'll take a 6-way PCB socket, and we're actually going to solder that to the underside of the board on the top 6 pins. So here's the Kickstarter development board with the header soldered on. Then we need an Uno. Now this is my old Uno that I've had for years. So you can I think you can use pretty much any Uno with this. Even the cheap Chinese copies will work for this function without any issues. But I have this one, so that's the one I'm going to use. And then we have the AVR ISP shield, as I showed you earlier. So if you have an Uno already, that's fine. If not, I think one of these is going to cost you like $3 or something for the Chinese copies. So this was around $2 and this is around 50 cents. So then what we do to actually make the programmer, all we do is we plug this guy onto the Uno, so it's just like a standard shield. And the reason that I actually use this is because it already incorporates the 3 LEDs that are recommended for this particular programmer. If you look onto the Arduino website or many YouTube videos or anywhere on the internet that will describe this process, it will encourage you to build a circuit on breadboard, and you will add 3 LEDs. One of those is for a heartbeat indication, one is for error indication, and the other is for programming indication. Now the reason I do it like this is because I found in the past that if you actually make one of these breadboard programmers, they may work okay for the first couple of times, but especially if you're developing an Attiny software where you can't actually have like a serial monitor easily and that kind of thing, or I don't know a way to do that anyway, you need to keep plugging the Attiny in and out a lot. And I found that if you make a breadboard programmer, they can become very unreliable after a time, and you might have a loose connection and not realize, and it's just a pain. So this way, for very little expense, you can actually make a custom programmer. So we just need to plug this onto the board like that. So it's the top 3 rows onto the 6 pins on that header, and that's it. We now have our programmer. So we can take an Attiny85, just quickly pop it into the socket, just like that. It doesn't have to be pushed in too hard, just a little bit. And then we can use this to program the Attiny85. We can actually download the software, we can download the bootloader and all that kind of stuff. So I'm going to show you how the programming for this works shortly, how to program the Uno, and then how to download programs to the Attiny. So I have already shot some footage with relation to the various components that I use to actually make the download. So I have actually showed you this board already, which is available on AliExpress, and I have already soldered on the 6-way connector onto that. So that is actually the programming socket itself. Now again, I have hopefully shown already the AVR ISP shield. Again, this is designed for Attiny the 328. So I think this is actually designed for programming the 328 or similar devices. So you can't actually plug the Attiny85 directly into one of these because the pins are not set up correctly, hence this board. So if you get one of these guys, which are available from AliExpress for next to nothing, and then you plug that onto the extension board on here, that will then enable you to plug an Attiny85 into here and program it directly from the Uno. So then we take that board and we plug that into the Uno, he says. Like that. So then to actually program the Uno itself with the software you need to turn it into an AVR programmer, we need to go over to the Arduino software again. So I shall just do that. Okay. Oh, first of all we need to set it to an Arduino Uno. Then you need to open the example sketch. So we go to File and then to Examples, and then we go to Arduino ISP and select that. That then opens the correct sketch. It's all predefined. So I'll just open that one up. We'll plug in the Uno. So as you can see, this is already programmed in. This is all you need. It's in the software. It's very straightforward, and all we need to do is to make sure we've got an Uno selected and then upload that sketch. It will compile the sketch here and then upload it. Yep. Okay, so that upload is complete. So that's the Uno is now programmed. Okay, now if I power that up, it's going to kind of be upside down, unfortunately. But there you go. So if I power that up, we can see that that we actually do have the LEDs on this board, the AVR ISP shield. So it's actually got LEDs that indicate a heartbeat, an error, and the fact that you're programming. Those LEDs are also replicated on this board as well. And I'll just what I'll do is I'll just plug in the Attiny85 that I've been using, and I'll show you the download process. Okay. This is the device that I've been using during the demonstrations on the video. So if I just plug that guy into here, I haven't got to push it all the way in by any means, just so it's in. So then I can, if I get up the Arduino, so I need to do, okay, so what I'll do, I'll plug this in so you can see. Okay, then I'll move over and I'll record the rest of it actually in the Arduino software. Once you have the Uno programmed with the AVR ISP software, that becomes a programmer. You can then plug your Attiny into the top socket. And once you have, what you'll need to do is to get these, if you look at this screenshot, you'll need to configure your Arduino software with all of these settings that you can see here. So that's the board, the chip, the clock source, the timer, the LTO, millis enabled, all of these the same. Okay, then you'll need, first of all, if it's a new Attiny85, you'll need to click on the Burn Bootloader button. Basically what that does is it just writes all of these settings onto the Attiny itself. Once you've done that, this is the program that I just showed you. So we just go on Sketch and then we click on Upload using Programmer. So what that does is it actually uses the USB connection to the Arduino Uno to program the Attiny itself. So we can click on that. We can see that it's saying uploading, upload done, and what I'll do is I will go back to the device itself, and I will now download that while you're looking at the device. So I'll just do exactly the same. So I'm going to click upload using programmer right here, and then you can see hopefully the lights are flashing to say that it's been programmed, and then it's complete. Yep, so it's complete when the light's gone off. Okay, so I can now unplug that, and I will take that device and I will plug it straight into the board here. Like that. Now I can power this up. And you can hear that it's gone into mode 3 straight away. So I do the short. Oh, I need to plug into that lead. Okay, we can do the short on that. Then if I plug it back into the diode tester, I'll do the reset. And then go into mode 4 by pressing the second button. And then I'll just quickly check a diode. Yeah, short circuit. Silicone diode. It's a short high frequency beep. And then we'll just get the Schottky diode. Short low frequency beep. So you can see that I've literally just program that and put it into the device, and you can see that working. I hope you enjoyed that video. If you enjoyed the video, please subscribe to the channel, it's much appreciated. Any comments, good or bad, I'd love to hear them. I'm happy to answer any questions that you might have on this device. Thanks for watching.